right. It is a new dawn. It is a new day and a new chapter. Chapter 2. And everything that you've been doing, everything that we've been doing so far, and all your math has been preparing you for this section. Right, this section, we're going to learn a concept called the derivative that is so core to maybe not necessarily all of mathematics, but definitely calculus, which calculus is a huge portion of mathematics. So, very deep concept. There's a lot to digest in this section. As you can see here, there are 18 slides. Don't be scared. If you need to take a break or something like that, please do that, because normally this is a topic that probably I would normally spend several days on in a traditional section. But we are not in a traditional setting, so you must figure out what works for you. All right, let's get started. Now, previously on business calculus, we have talked about the average rate of change. All right, we have done several exercises to get you comfortable with the idea of finding the average rate of change between 2 points. So we have a graph, and we find the difference in the y values, divide by the difference in the x values, and that'll give us the slope of a line between 2 points. Okay. Now, this line between 2 points, this is called the secant line. This is called the secant line. It's not so important, but it could, you might see it from time to time, so you should know what it means. It's just a line on the graph that that passes through like 2 points. Okay. So we have found the slope of the secant line, all right, to give us the average rate of change. All right. Now we're going to talk about slope at a point. All right. So no longer do we need 2 points. This is absurd. How can we find a slope at 1 point? How can we only need 1 point? Well, let me go back for just a second. What would happen if we use the slope formula for 1 point? What if the x-coordinate was the same? We would, all right, what if my two x-coordinates that I chose were the same, both a? Well, on the denominator here, I would have a minus a, which is 0, and so I'd be dividing by 0. And that's bad. That's bad. In math, we always have to worry about dividing by 0. Every class you ever take, you'll have to worry about it. So we're going to get around that, though. We're going to get around that. So that's not what we're talking about here. We have a more clever approach that we're going to show you. All right, so with slope at a point, how are we going to find this? How are we going to define this notion? All right, so what we're going to do is we're going to bring the 2 points that we use on the slope formula, we're going to bring those very close to each other. Very close to the point that we actually care about. So for example, let's say we have the function f of x equals x squared minus 1. This is the graph of the function. It's an upward opening parabola. Y-intercept is minus 1. All right, this is just the portion that we care about for the graph. And let's say we want to find the slope at x equals 0. So that's this point here, x minus 1. 0 comma minus 1, this point on the graph, and we want to find the slope at this point. That's because we want an idea of how this function is behaving at this particular point. All right, and so what we're going to do is we're going to define the slope at this point to be the slope of what's called the tangent line, which is the line that only passes through 1 point on the curve. So notice this this line here, this yellow line, it just grazes the curve. Right? It just passes through 1 point, this bottommost point in this case. If we were to tilt this line up maybe slightly, then it would pass through more than 1 point. Okay, so there's something special about the tangent line to the curve. Just passes through 1 point. All right, it's a special, there's only one of them, tangent line. And we want to find the slope of that line. And that's how we're going to define the slope at a single point. All right, so what does that mean for us in our exercises, and hopefully it'll make more sense for us. Well, first, we need to remember a concept that we talked about before, that what's the relationship between the rate of change and the actual slope of a function. Remember, we've talked about what it means for a function to be decreasing. That means it's going down from left to right. And that means its slope, the slope between 2 points in that region, will be negative. All right. Decreasing does not mean the same thing as negative, but for a decreasing function, its slope is negative. All right, slope between 2 points or slope at a point in that area should be negative. All right, we'll pin this down more concretely later, but I just wanted to share it with you now. It's not a big slide, but it is a very important one. I just want you to understand this box for the moment. So when we have a constant function, what does that look like? That looks like a horizontal line. Constant function is a horizontal line. That function will have slope 0. Horizontal lines have slope 0. Difference in the y values is 0 divided by some change in x coordinate, that's 0. Increasing functions have positive slope. All right, so keep that in mind. All right, now let's go step by step and find the slope. Back to our example and find the slope at x equals 0. So we want to find the slope at x equals 0. First, we'll choose two x coordinates, one of them being 0, and the second one will be 1, and we'll find the slope between those 2 points. And what I get is 1. All right, so these are the 2 points. When I make the line between them and I find the slope of that line, I get 1. That's just our slope formula. All right, now I'm going to bring that second coordinate, point 1, I'm going to bring it closer, much closer, to the point that I actually care about, which is x equals 0. So instead of x equals 1, I'm going to use x equals 0.1. And when I make the line between those 2 points and find that slope, all right, using our slope formula again, I get 0.1, not 1, but 0.1. And notice as I bring this point closer, this line that I make, it's becoming more horizontal, isn't it? It's becoming more horizontal. Okay, now I'm going to bring it even closer. I'm going to bring that coordinate 0.1, I'm going to bring it even closer to 0.01, very close to x equals 0. So I'm finding the slope between 2 points that are very close to each other. All right, and I use the slope formula, and in that case I get 0.01 after I do everything. All right, so we notice a pattern anytime. We're always looking for patterns in math, and let's see if we can spot the pattern here. 1, 0.1, and 0.01. If we keep doing this process, if we keep getting closer and closer to x equals 0 for our second point, notice what the slopes are doing. They're also getting closer to 0. The slopes are getting closer to 0. So the slope at that point is 0 because we notice the pattern. The pattern is going to 0. All right. So what we have now is it's a rough way to find the slope at a point. Right? So we'll find the slope between 2 points, but we'll make both points very close to the point that we actually care about. And we'll notice a pattern, and there will always be a pattern. Okay. This is not the way that we will do it later on. We'll have a little bit faster way to do it, because notice this is a lot of calculating involved. We'll actually have a way to bypass this calculation. So if this feels like a lot, well, just do it for now. You won't have to do it forever. We all have to, every math student, we have to go through this. these lots of formulas and spot the pattern, but later on we'll have a way to make it cleaner. Okay, so we have a way to do it. We've got our foot in the door. That's what we care about. All right, we have a way to do it. So may not be the fastest way, but we have a way to do it. We find the slope between 2 points and we make them very close to each other. All right, now here's the thing. The subtle point is that when we do this for each x value, we do this process for each x value, what we get is another function. All right, so we had the function f of x, and we can actually do this process of finding the slope at each point, and the slope is a number, right? So what we get is another function. That function is called the derivative of f of x, and the way we write it is f prime of x. Right, we just put a little apostrophe symbol there, kind of like an apostrophe. So, all right, it's the same key on the keyboard, for example. Okay, so yeah, we get another function. It's called the derivative of fx. It represents the slope at each point, but it's quite cumbersome to say slope at a point. Sometimes you see the term instantaneous rate of change, which we won't use very often. We will just say the derivative of f of x. That's what we normally say. All right. So what we've done, this process of finding the slopes between each point, or between 2 points that are close, closer and closer. This is called numerically estimating the derivative, doing these calculations and trying to spot a pattern. All right, so we have a way to do it. Okay, if your head's not spinning so far, let's continue and see another example to put another point on your graph of understanding. Okay, bad jokes. All right, so what is the derivative of the function f of x equals e to the x, this time at x equals 1? Before we found the derivative at x equals 0. How about when x equals 1? Well, I will do the same thing that I did before. I'll find the slope between 2 points, and I'll make my second point close to 1. So like 1.1, that's close to 1. And I'll find the slope, and then I'll do it again, but I'll make my second point even closer to 1. So 1.01. I'll find the slope, and I keep doing this process, and I get closer and closer, bring those 2 points closer and closer, and finally I see the pattern that the slopes actually get close to one number, which is good. They get close to the number 2.72 after you round it to 2 decimal places. These numbers are all rounded. All right, so that is the derivative at x equals 1. All right, this is not f of x, this is the slope of f of x at x equals 1. That is 2.72. It's a slope, but we call it the derivative. All right, so that's that. Now, it's important not only to be able to do the formulas and stuff like that, but also a thing that a lot of people are not comfortable with, that we need to work on, is understanding what we did in a graphical setting. So like, what's like a picture that explains what we did? It's like the other side of the story, right? You do formulas, that's great. It's important. You get your foot in the door, but we should also keep in mind the graph, like some sort of picture of what we did, so that it'll make our understanding sort of more complete. Okay, so what we just did was we found the slope of the function f of x equals e to the x at x equals 1. So here's this function e to the x, this blue curve here, and if we were to make the tangent line, the line that only passes through one point, it just grazes the curve at x equals 1, and we were to find the slope of that line, then that's what we would get, the 2.72, the number that we calculated. All right, So the slope at that point is the same as the slope of this line, this tangent line, at that point. Okay? So that's that. All right, so now we're going to recall what we talked about before. We talked about what it means for a function to be positive, and we said that a function is positive if the y values are positive, right? And that means that the graph lies above the x-axis. And a function is negative if the y values are negative, which means the function lies below the x-axis. And it's 0 at the points where it crosses through the x-axis. All right. So whether a function is positive, negative, or 0, it depends on the x-coordinate, right? At each x-coordinate, it may be negative, it may be 0, it may be positive, and so forth. Okay. We also talked about, like, the next level, whether a function is increasing or decreasing, right? And we said that a function is increasing if going from left to right, the function is going up. All right. And then we said the function is decreasing if going from left to right, the function is going down. All right. And then notice that this also depends on the x-coordinate, right? Some x-coordinates you choose, like x equals -1, the function is clearly increasing. It's going up from left to right at that point. X equals 2, it's clearly going down from left to right. It's going down, which means the slope is negative. All right. The slope is negative, but the function is not negative. But the function is decreasing. Okay. So now we have a more precise way to write what it means for a function to be increasing, because we have a way to get the slope at each point. All right, so now I can talk about a function increasing at x equals -1 in terms of its derivative. All right, if its derivative is positive, meaning its slope is positive, that's what we mean by the function increasing. Similarly, a function is decreasing when its slope at that point, which we don't normally say slope at a point, I'm just doing it because we're getting used to it, meaning its derivative at that x-coordinate is negative. Decreasing means the derivative is negative. All right. And another thing to notice is that we always have these in-between values, like this point here, this bottom value. See, it's not decreasing, it's not increasing, it's in between. And what would be in between decreasing and increasing? That would be remaining the same, constant. It's not changing at all. It's changing by 0. All right. So these are points to look for. These give us points to look for maxes and mins. Not sure that made sense. Points where the slope is 0 or where the function is sort of constant, it's not changing, those are often maxes and mins of the function. All right, I didn't do a very good job of explaining that, but hopefully some of that made sense. All right, so this is a slightly modified version of that little table that I showed earlier. So remember that a function decreasing, that means the slope is negative. Well, now I just labeled what the function is. Say the function is f of x. Well, now we have a notion of what the derivative is, and we call that f prime of x. So if f of x is decreasing, that means the slope or the derivative is negative. If the function is constant, the derivative is 0. And if the function is increasing, that means the derivative is positive. All right? Sometimes it takes a while to, for our mind to get used to making these distinctions between things like decreasing and negative. All right, we don't really understand what's the difference between decreasing and negative. It seems like the same thing. So the best thing we can do is just kind of keep trying and until it kind of clicks for us. But eventually it will. Practicing making these distinctions, because they are two different concepts, and they are related in this way. All right, so that's that. Okay, now that is the hard part. I mean, that is the hard part of the lecture. I mean, we're done with like hard conceptual stuff, and in fact, that's the hardest part of the whole semester. So if you made it through so far, you should feel good about it, because after this point, conceptually, it won't get more difficult. I don't think. We're just building on what we've done before. This is the most subtle concept, and it's one of the most subtle concepts for math students that math students ever encounter. So it takes many, many years to kind of get to the point where they can kind of grasp it. But let's see some more concrete examples. Take a step down a little bit before we end the lecture. So help you with your Wiley plus problems. So remember we talked about before the distance function s of t. That's the distance that some object has traveled at time t, and the slope of the distance function between 2 points, we call that average velocity. It's the average rate of change, but that rate of change we'll call velocity. All right, so we've done this before. Average rate of change is the slope between 2 points. We use the slope formula. So for example, if you drove 200 miles in 5 hours, we'd say that on average, you were driving, take the difference in the distances, divide by the difference in the times, and you get 40 miles an hour. Okay, so that's average velocity. And now what we're going to do is we have a notion of instantaneous velocity. Not velocity between 2 times average velocity, but a velocity at a particular time. And actually, normally we just call this velocity. We can just drop the average because we can figure out how fast an object is moving at a particular point in time, because now we have a notion of that, right? We have a concept of that. It's clearly preferable to be able to talk about a velocity at a particular moment in time than to have to describe how fast it was going between 2 times. All right, so we will estimate this the same way that we in our previous examples. We'll bring the 2 points, we'll find the velocity between 2 points, but we'll bring them very close to each other. So for example, if we have the distance function, which it's the same one for the previous example. I guess the previous one was s was measured in miles. So this function is measured in feet, that the object has traveled, some object has traveled in t seconds. And this time we have a formula for the distance traveled. All right, so the instantaneous velocity at t equals 2, what we'll do is just find the average velocity between 2 points that are very close to 2, where the x-coordinates, the t values are very close to 2. And when I do that, when I make them closer and closer, I see that I get numbers, slopes, that are getting closer and closer to 12, aren't they? So if I made the slope between, so you see that I have here when t gets closer to 2, so it's 2.001, 2.00001. What do you think would happen if I chose 2.00001? Well, I would probably get a slope of 12.00006, right? Just add 0. So we would just have more zeros. So you see that really what's going on here is the slope is like 12. Okay, so the velocity at this particular time, 2, is 12. And how do we measure velocity? We measure it in feet per second, because the height function was measured in, or the distance function was measured in feet. Right? Sometimes we call the derivative of the distance function, we just call that v for velocity. Nice and easy. Right, here's a graph of the velocity function. Here's a graph of t cubed, by the way. This actually curves downward like this for the negative x values, but over here it looks kind of similar to the graph t squared. All right, so that's that. And an even easier example is if let's say I throw a ball up in the air, and we're given a table of heights of a ball at time t. So here's the table, and let's say we want to know the velocity at a particular point, t equals 1, for example. Well, unfortunately, I don't know what the y values are for x values close to 1, very close to 1. So I can't use the same technique I used before where I plug in t equals 1 and 1.1, 1.01, 1.001, and so forth, because I don't know the y values. I won't be able to do the full formula. So the best that I could do is choose the time closest to 1. So maybe time equals 2. Time equals 1 and time equals 2. So I will find the slope between these 2 points, and that will be the best estimate, about the best estimate that I could do. You might say, why don't you use time equals 0 and time equals 1? Why did you use 2? It really doesn't matter that much. Both are fine. Both are fine. They'll both give you an estimate. Let's see, you would have 4 compared to 5, 4 feet per second compared to 5 feet per second. We're talking estimates here. It's the best we could do. Either one is just as reasonable as the other. All right. So if you made it through all that, you really should pat yourself on the back, because this stuff is not easy. It's like I said, it's the subtlest concepts that many math students ever encounter, and it's sort of the foundation for all of calculus, what we're talking about here. And so hope some of it made sense at least, and hopefully more of it will make sense on your Wiley Plus homework, and good luck with that. And of course you can always email me. You could stop by office hours, even though no one did last time, but who knows, it may happen. So I'll be there. All right, with that, goodbye.